guys, I'm back with another video. Today we're going to be going over inclined planes and also a little bit more of some one-dimensional kinematics. Okay, so let's just go ahead and start with number one right here. Number one says a 4-kilogram box is placed at the top of a frictionless inclined plane that makes a 30-degree angle with the horizontal. The box is released from rest at the top of the incline, which is 5 meters long. So we want to know the acceleration of the box as it slides down the incline, how long does it take for the box to reach the bottom of the incline, and what is the velocity of the box when it reaches the bottom. All right, so now we know what we want to do. So the first thing I like to do whenever we have an inclined plane problem is just go ahead and just establish my X and Y axis. So I'll just go ahead, I'll just make a note over here in the corner. Ooh. Make a note over here in the corner. This direction is X. This direction will be Y. That way when we add up our net force, we'll know positives and negatives. The second thing I like to do is draw a free body diagram so I can get a good picture of all the forces acting on this box. So remember, our weight force is always straight down, no matter if we're on the incline or not. Okay, so this weight force, remember, is mg. So mg. Then we'll have a normal force that's perpendicular to the surface. So our normal force will look something like this. Ooh, that's bad. Hang on, let me fix that. Okay. Need to make a better drawing here. That's better. That's better. Okay, so this is our normal force, or F of n. Then we have a gravitational force that is pulling our box down this incline. So that will be going in this direction right here, in the positive X direction. We can call that F of G. Okay, so how do I want to start this? Well, I know that this line right here can be broken down into components because we are at an angle which is theta. I should have drawn this at the beginning. So theta is going to be 30 degrees. I'll go ahead and just write 30 degrees. Okay, so this can be broken down into X and Y components right here. So I'll just draw a dotted line as best as I can. Okay, so this magnitude of Fn is equal to this imaginary line we drew right here. Well, in relation to theta right here, which is 30 degrees, this is mg cosine theta. Theta, okay. And this one right here, this component would be mg sine theta. Okay. So we need to find our normal force and we need to find our gravitational force. All right, in order to do that, though, we need to just go ahead and establish what mg is. So I'm going to go over here to the top right. Okay, we know our mass of our box. We know gravity is 9.8. So our mass is going to be 4 times 9.8. That's going to equal 39.2 newtons. Okay. Now we can find our normal force as well. Now that we know mg, we'll find our normal force. Remember, normal force is mg cosine theta. Okay, so that equals mg cosine theta. Well, we know mg is 39.2. Okay, 39.2 times cosine of 30 degrees. Okay, and that will give us 19.6 newtons for our normal force. Okay, so now we can figure out our only force that's moving in the x direction. Remember, this box is not moving up and down in the y direction, so those two forces will cancel out. Okay, all the net forces in the y direction will cancel out. So our box is only moving in the horizontal x direction. So we really need to establish that f of g is equal to our net force in the x direction, which net force can be described as mass times acceleration. So we'll just write it as max. Okay. Well, f of g is equal to mg sine theta. So we can rewrite this as mg sine theta, which is going to end up being, it's equal to max, or our net force in the x direction. Okay, so these masses can cancel out, and now we're left with g sine theta is equal to our acceleration in the x direction, which is the only direction this box is moving. So we can just go ahead and write that out, and we'll erase some of the top stuff. Rewrite it up here at the top. Okay, so g sine theta is going to be 9.8 times sine of 30 equals our acceleration in the x direction. All right, so all right, our accelerations are going to end up being 9.8 times sine of 30. Let me type this in my calculator real quick. Okay, 9.8 times sine of 30. Where's my close parenthesis? There it is. Okay, and we will get 4.9 meters per second squared. So that is how fast our box is moving down this ramp. Okay. Now we can start using kinematic equations to help us solve for B and C. So let's go ahead and erase, clear up some room for us here. Sorry about the bad handwriting. Hopefully my talking can get you through it. Okay, so the formula I want to use, first off, let's remind ourselves, the answer to A was 4.9 meters per second. Meters per second squared. Okay. Now the formula I want to use for B is going to be distance is equal to initial velocity times time plus 1/2 times acceleration times time squared. Okay, let's plug in some numbers. 5, because remember from our question it says the ramp is 5 meters long, equals 0 because our box starts from rest, plus 1/2 times 4.9, because remember that's what we got from our answer in A, our acceleration, times t squared. Okay, so all I have to do is solve for t squared, and I should end up with t squared equals 5 divided by 2.45. 2.45. Okay, square root both sides. Square root this side. We should get t is equal to 1.43 seconds. 1.43 seconds. So that will be the answer to part B. All right. Lastly, we want to know what is the velocity of the box when it reaches the bottom. Okay, so let's go ahead and erase. Clear us up some room. All right, I'm going to rewrite what we know now is 1.43 seconds to reach the bottom. So now let's finish up and answer B. So this equation I want to use is going to be V final. Our final velocity equals our initial velocity plus our acceleration times time. Pretty simple formula. So V, we're solving for our final velocity at the bottom, is going to equal 0 because our box starts from at rest, plus acceleration, which is 4.9, times 1.43. That's how long it takes to reach the bottom. And that will give us 7 meters per second. That is the answer to C. All right, so that's how you solve number 1. Let's go ahead and clear our work and move on to number 2. Okay. Let's move on to number 2. Okay. All right, number 2. Number 2, let's go ahead and establish our x and y coordinates again. I'm just going to keep them the same. I always keep them the same just to have continuity. So y is going to be this direction, x will be this direction. All right. A student gives a 3 kilogram box an initial push so that it slides up a frictionless inclined plane at an angle of 25 degrees with an initial velocity of 6 meters per second. What is the acceleration of the box while it slides up the incline? How far up the incline does the box travel before coming to rest? How long does it take for the box to come to a stop? All right, so first, as always, let's draw a picture. Anytime we're dealing with forces, let's just draw a picture. Okay, so we have our weight force going straight down. We have our normal force that's perpendicular to the surface. we have our little imaginary triangle that we can draw to help us derive our formulas. Okay, this is going to be mg. All right, this will be mg sine. We'll put theta here. That is theta. Theta is going to be 25 degrees. There. Degrees. All right, so this will be mg sine theta. And this will be mg cosine theta. And we also have one more force. That's going to be the gravitational force pulling the box down the ramp. Okay, first thing we can do is go ahead and just solve for mg that's given in our problem. So mg is going to equal 9.8 times 3. That's going to give us 29.4 newtons. Now we want to know the acceleration of the box. Okay, so we want to know the acceleration of the box. So we can say that the net force in the x direction is equal to mg because we only have one force going in the x direction. This box is not moving up and down vertically on the ramp, it's only moving horizontal, and we only have one force acting on it since we have a frictionless surface. So we can say that the sum, our net force in the x direction is equal to f of g, or we could rewrite it as the mass times acceleration in the x direction is equal to the negative, I forgot to put negative because we got to respect our x and y coordinate system we established, negative mg sine theta. Okay, we can go ahead and cross out the mass in here, and we can go ahead and establish that the acceleration in the x direction is equal to negative g sine theta. Okay, now we can start plugging in numbers. So we know g is going to be negative 9.8 sine of theta times sine of 25 degrees. So when I plug that in, I should get the acceleration of the box in the x direction is negative 4.1 meters per second squared. Okay. So the negative, all it's telling us is that the box is accelerating back down the ramp. Okay, let's move on to the second part of this problem. Let's move on to B. Let me rewrite that piece of information up here so we don't forget it. Negative 4.1 meters per second squared. Okay, so we gave the box an initial push up the ramp and it's slowing down, it's decelerating at a rate of negative 4.1 meters per second. So now we want to know how far up the incline does the box travel before coming to rest. So there will be a point after we push this box up the ramp where it will stop and then start to come back down the ramp. Okay, so we want to find that point. So we want to find distance. The formula you can use here, one of the kinematic formulas you can use is VF squared, or final velocity squared, equals the initial velocity squared plus 2AD. All right. We want to know when the final velocity is 0 because we want to know at which point is the box stopped. So we can say that the box stops. When the box stops, it has 0 velocity, and we know that it's given an initial push of 6 meters per second. So we can do 6 squared plus 2 times negative 4.1, because we know our acceleration now, times d, distance. So we rearrange this formula and solve for d. We should get d equals negative 36 divided by negative 8.2, and we should get a positive 4.39 meters. 4.39 meters. Okay, again, I just rearranged the formula to solve for d. Okay, so now we know the distance, how far up this ramp this box will travel before it starts to come back down. So let's go ahead and erase. Let's move on to part C. I'm going to go ahead and rewrite 4.39 meters. That's how far we travel up the incline. How long does it take for the box to come to a stop? So now I want to use this kinematic formula right here. So I want to use final velocity is equal to initial plus our acceleration times time. So we know our final velocity is 0 when it comes to a stop. So 0 equals, and we already know our initial velocity is 6 because that's given in the problem, plus negative 4.1. So we derive that from part A, times time. So now we go ahead and solve. We get negative 6 divided by negative 4.1 equals t. T is going to equal 1.5 seconds. So that is the answer to part C, 1.5 seconds. All right, let's go ahead and move on. Now we're going to start getting into the problems that have friction. Erase all this before we move on. All right, let's see. Nope, don't want that. Okay, a 5 kilogram crate is released from rest at the top of a 6 meter long incline that makes a 35-degree angle with the horizontal. The coefficient of kinetic friction between the box and the incline is 0.2. We want to know the net acceleration as the crate slides down the incline, how long does it take to reach the bottom of the incline, and what is the final velocity of the crate. So let's do as we always do. Establish our x and y coordinate system. So x will be this direction, y will be in this direction. Okay. Now let's draw a free body diagram. So I'm just going to draw all the forces acting on this crate. So we have a weight force, that's mg. We have a normal force. We have the force of gravity pulling the box down. And then we have kinetic friction opposing the motion of the box. So I'm just going to call that our friction force. Okay, so first thing I want to do, I want to go ahead and just solve for mg. Let's go ahead and knock that variable out of the way. So mg, mass times gravity, 5 times 9.8, that's going to give me 24.5. Oops, sorry, reading the wrong one. It's going to be 49. 49 newtons. Okay, that's 9.8 times 5, 49 newtons. The next thing I want to do is just go ahead and look, let's get the sum of all the forces in the x direction. Remember, our box is not moving up and down on the incline, it's just moving in the x direction. So our sum of forces in the x direction, we will have F of g, which is in the positive, minus our friction force, because that is in the negative x direction. So let's go ahead and rewrite that. So we have mass times acceleration in the x direction is equal to mass times g sine of theta, mg sine theta, because that's what Fg is equal to if we did our little imaginary triangle right here, minus the normal force times the coefficient of friction. But remember, our normal force is equal to mg cosine theta times, I'm going to go ahead and write 0.2. 0.2, that's the coefficient of friction that's given. So one thing we can do, we can just go ahead and cross out all of these mass variables. The next thing we can do, we can go ahead and just solve for acceleration, because I think we have all of these values. Let me go ahead and write 35 degrees as our theta here. All right, 9.8 times sine of 35 minus 9.8 times cosine of 35 times 0.2. Okay, so we should end up with our, when we multiply those two values out, we should get 5.6 minus 1.6, which will give us an acceleration value of 4 meters per second squared. That's in the positive direction, so our box is accelerating in this direction right here. So that is the answer to A. All right, let's move on to B. I'll rewrite the answer to A up top, clear out some space here. How long does it take to reach the bottom of the incline? All right, so for this problem, we can use our distance formula. Distance is equal to initial velocity times time plus 1/2 times acceleration times time squared. Let's rewrite some numbers here. We know that the incline is 6 meters long. We know our initial velocity start at rest, so that variable will be 0 plus 1/2 times 4 times t squared. So let's go ahead and solve for t here. We can get 4 sorry, not, yeah. 1/2 times 4 is 2. 6 divided by 2 is 3. 3 is equal to t squared. Square root both sides. The square root of 3 is going to be 1.7. So t is going to be 1.7 seconds. So now we know how long it takes for the box to reach the bottom of the incline. .7 seconds. Lastly, they want to know the final velocity. So for this, I'm going to use VF. Final velocity is equal to initial velocity plus acceleration times time. It's a bad A. Acceleration times time. So VF is going to be equal to 0 plus 4 times 1.7. And we should get VF is equal to 6.8 meters per second as the speed when the box reaches the bottom of the incline. Okay, let's move on to the last question here. Let me erase everything. Moving on to the last question. It says a 2.5 kilogram box is given an initial velocity of 4.0 meters per second up a 30-degree incline. The coefficient of friction between the box and the plane is 0.15. We will know the net acceleration of the box as it slides up the incline. How far up the incline does the box go before stopping? How long does it take to come to a stop? Let's go ahead and establish our X and Y coordinate system. Keep it the same. Second, let's draw a picture. We have mg going straight down. Next, we have our normal force. Then we have our gravitational force, F of g, pulling the box down. And then we have our kinetic force, or friction force, sorry. Our friction force also opposing the motion of the box. So remember, the box is sliding up the ramp here. Okay, so this is what your force diagram should look like. Okay, first thing we can solve for, mg, always. Always can solve for mg. mg is going, here will equal 24.5. So we took 2.5 times 9.8. We get 24.5 newtons. Now let's talk about the sum of our x forces. So the sum of our forces in the x direction is going to be negative F F of G, force of gravity, minus our friction force. Because you can see both of these forces are moving in our x direction, negative x direction according to our coordinate system. This equation can be written as mass times acceleration in the x direction is equal to negative g of mg sine theta minus mg cosine theta times the coefficient of friction, which is 0.15. Let's go ahead and write that in. So we can go ahead and take out our mass. So now we're left with our acceleration is equal to negative 9.8 times sine of 30. Go ahead and write down there. 30 minus 9.8 cosine of 30 times 0.15. Okay, so we have our acceleration formula set up. We just plug all those numbers in. You get negative 4.9 minus negative 1.3, so just minus 1.3. When you plug in these two different factors into your calculator, variables into your calculator, and we are left with the acceleration in the x direction is going to be negative 6.2 meters per second squared. So that is the answer to A. Part A. It's going to also help us with our kinematic equations. I'm going to rewrite that answer up here, clear out some more space. Negative 6.2 meters per second squared. Now, part B, how far up the incline does the box go before stopping? All right, for this problem, I'm going to use, for this kinematic equation, final velocity squared is equal to initial velocity squared plus 2 AD. All right. Well, we know that our final velocity is 0 wherever we stop on the incline. Our initial velocity is given to us in the problem, and it's going to be 4. So we do 4 squared plus 2 times negative 6.2 times d. So we're going to have d is equal to negative 16 divided by negative 12.4. And that answer will give us 1.3 meters. 1.3 meters. So that's how far up the incline the box will go before stopping. So let's clear out some more space and finish up this problem. 1.3 meters. How long does it take to come to a stop? All right, for this problem, we are going to use the following formula. We're going to use final velocity is equal to initial velocity plus acceleration times time. Okay, so our initial velocity when it comes to the stop, or sorry, our final velocity is going to be 0. Our initial velocity was 4 plus negative 6.2 times time. We plug this in the calculator. Okay, we get negative 4 divided by 6.2, negative 6.2, and you should get t equals negative 4 divided by negative 6.2, and you'll get t is equal to 0.65 seconds. That is the answer to C. So that's how long the box will travel up the ramp until it comes to a stop. Okay, I hope you found this video helpful. If you need extra help, come talk to me during class time or shoot me an email. I apologize about the handwriting. Hopefully my talking kind of helped you through it. I'm still trying to learn how this Wacom system works, but hope you have a great rest of your day. See you in the next video.